Good day, ladies and gentlemen. You are welcome to our lecture number 2 on Eten407, that is Introduction to Semiconductors Microelectronics. And today's lecture we'll be looking at quantum mechanics, introduction to quantum mechanics. The first question that we need to answer here is, if we are asked, why do we need to study quantum mechanics? The answer should be like this. When you use classical mechanics, that is the ordinary mechanics we are used to, the laws like Newton's laws of motion, like Maxwell's equations of electromagnetics theory, and the related formulas which we are used to in physics, whenever you limit yourself to these formulas, you are going to be studying macroscopic phenomena. That is the phenomenon that is in macro size, that is the big size that can be analyzed with ease. But whenever you want to study those microscopic phenomena, that is the phenomena that are too small for this classical mechanics laws to take care of, you have to study quantum mechanics, because it will help you to explain and understand the microscopic phenomena such as photon atom scattering and the flow of electrons in the semiconductors. For you to critically and clearly understand this phenomenon, which are in microscopic scale, you have to study quantum mechanics, and therefore that is the reason why we need to study quantum mechanics. So what is quantum mechanics? We can simply define it as a collection of postulates. You know, the stages of creating law in physics and in science in general. We have hypothesis, then we move to a postulate, we move to law, and that law, when it is finally accepted, it is a law and it can be a principle. So quantum mechanics is a collection of postulates which are obtained or which are made from a large number of experimental observations. That is, scientists will carry out experiments based on what they observed. They come up with a postulate. So collection of this postulate is what we call the quantum mechanics. Then the next thing we need to understand under quantum mechanics is, what is a system? If we say a system in quantum mechanics, it is simply a collection of particles, and these particles, they can interact among themselves when they are using internal energy, and they can also interact with some external world, that is other components which are not within that system, but this time around they have to use external energy. So this is what we call a system in quantum mechanics. So the next thing we look at is what they call wave-particle duality. We know a wave has a property entirely different from that of a particle. For instance, a particle has mass, whereas the wave don't. The particles sometimes do have charge, positive or negative, but the wave don't. But it has been established that sometimes you can have a particle behaving like a wave, or you can have a wave behaving like a particle, and that is what we call the wave-particle duality. So under this, a quantum state, if we say a quantum state with respect to this wave-particle duality, is a collection of several possible outcomes of a measurement on a physical system. Whenever you take a measurement on either particles or wave, the possible result that may come out, the collection of that is what we call a quantum state. And the quantum mechanics uses the language of probability for us to clearly understand, because in science and engineering we have two methods. We have what we call deterministic, that is something that knows the actual values, and we have what we call stochastic or probabilistic, something that you are not sure about. The result can be 1 and it can be -1, it can be anything. Therefore, in quantum mechanics, we are using the probability theory, not deterministic theory, where we actually know what is supposed to be as the output of our measurement. So under this quantum mechanics also, we have to understand what is uncertainty principle. And this one also, the uncertainty comes of whenever or when they establish that you as an observer, you cannot observe the microscopic system without altering some of its properties. Meaning, if you observe one aspect of this microscopic system correctly, the other one that is supposed to be together with it, you have to get an error. That is the alteration they are talking about. They are also saying you cannot predict how the state of a system will change, because we said we are using probability theorem, not deterministic method. So based on this knowledge that you cannot get all the measurement correctly, then we come up with what we call the uncertainty principle. And this is a principle stated by a scientist called Heisenberg, and the principle is called Heisenberg uncertainty principle. What he said is this: one cannot accurately specify the values of the particle position and its momentum at the same time when you are limited to microscopic particle, that is a quantum mechanics. So if delta x is the possible error you are going to make when measuring the distance, and delta p is the error that will be encountered when measuring the momentum, then the product of the two, according to Heisenberg uncertainty principle, must be greater than or equal to 1 over 2h over 2 pi. Sometimes they just take 1 over 2h, and sometimes they put this 2 pi wherever, because everything you've seen here is a constant, because the h is also a Planck's constant. It is a constant. Now we look at what they call correspondence principle, and this is to explain to us that whenever you limit your quantum mechanics to the study of microscopic system, that is the large systems that can be vividly seen, then you are no longer using quantum physics, but rather you are dealing with classical physics. We have seen it from the beginning, that the reason why we need quantum mechanics is for us to be able to study microscopic phenomena, because the classical physics is limited to macroscopic. So whenever you are using quantum mechanics to study microscopic, then you are reducing yourself back to the classical physics, not quantum physics. Therefore, non-classical phenomena, that is microscopic phenomena like uncertainty, like the duality we have just seen, they cannot be detected. You cannot study them whenever you are using microscopic system. And as we have explained previously, that is the reason why we have to use quantum physics if we want to study the microscopic realities like uncertainty principle, like the duality of wave and particle, and the rest. Then the other thing which is relevant to quantum physics or quantum mechanics is what they call the black body radiation. From our elementary physics, we know that there is what is called thermionic emission. That is, whenever you heat a material, that material can radiate heat, and of course sometimes it can radiate electrons, and those electrons are called thermionic electrons. And of course, the heat that is being radiated from the hot body, its color depends on the temperature range. For instance, whenever the temperature reaches 550 degrees Celsius, the light that will come out as radiation is dark red. But when the temperature reaches 700 degrees Celsius, it will now be red, but this time around it is bright, not dark. And of course, after 700, it can change to orange, it will change to yellow, and finally it will give you a white light when the temperature reaches the highest possible level. Another formula or law which is relevant to quantum physics is what they call Wien's displacement law. And this law is saying that the intensity, that is this sigma, with respect to lambda and T, where lambda is the wavelength and the T is the temperature, they said this is the total radiated power per unit area whenever a body is heated. And this formula, it is telling us that the radiated power is a function of wavelength lambda and the temperature. So the Wien's displacement law says the maximum of the distribution shifts to smaller wavelengths as the temperature is increased. The product of the wavelength, because we said the intensity is a function of wavelengths and the temperature, so the product of the wavelength, the maximum value, and the temperature is equal to this 2.898 times 10 raised to the power minus 3 meter Kelvin. Remember, the unit of a wavelength is meter and the unit of temperature is Kelvin. So the unit of the product of two should be meter Kelvin. And the wavelengths that are possible with respect to the type of light we are studying. If it is visible light, the range is from 400 to 700 nanometer. For ultraviolet, less than 400. For infrared, more than 700. So the next law is what they call Stefan-Boltzmann's law. And the law is saying that the total radiated power increases with the temperature. That is, whenever temperature increases, the radiated power R of T increase, and the total value we get is the integral from 0 to infinity of that function, that is the intensity we have just seen with respect to wavelength and the temperature, and we are doing the integration with respect to wavelength. And the value of this, the approximate value, is equal to epsilon sigma T raised to the power 4, and this T raised to the power 4 is proving that the total power is increasing with the increase in temperature. And this epsilon, this is known as the Stefans-Boltzmann's law, this equation, and the constant, this sigma, it has a value of 5.607 times 10 raised to the power minus 3 watt per meter square Kelvin raised to the power 4. And the epsilon here is called emissivity, and this emissivity is equal to 1 if you are using ideal black body. We know the ideal black body is the body that will radiate all the energy or absorb all the radiant energy to itself. But when it is not this ideal, you find that the value of this epsilon is always less than 1, and it is the ratio of the emissivity of the particular body divided by that of a black body, which is 1, and the value should always be less than 1. So in continuation of studying the quantum mechanics, we look at what they call Rayleigh law. This scientist, Lord Rayleigh, he proposes a formula for the radiation intensity we have just seen, and he set the formula for this radiation intensity, which is a function of wavelength and temperature, as we have already seen, is equal to 2 pi c kt all over lambda raised to the power 4. 2 pi we know constant, c is the speed of light, and k is the temperature, the Boltzmann's constant, and t is the temperature in Kelvin, and lambda is the wavelength in meter, as we all know. So this is what we call the Rayleigh law with respect to radiation intensity. Now we come to the hypothesis by de Broglie. De Broglie is also another scientist who made a contribution to this quantum mechanics, and he suggested that whenever you have a wave of wavelength lambda, they can be associated with particle that has momentum. That is the wave-particle duality principle. That is, you can have a wave that has a wavelength, and at the same time it has a momentum. You know, the wavelength is a property of wave, but the momentum is the property of particle. So if we have that duality, he said the momentum of that wave is equal to h over lambda, where h is the Planck's constant and lambda is the wavelength of that wave. And he said it can also work the other way around. That is, you can have a particle that behaves like a wave, so that one also will have its momentum with respect to its mass and the velocity, and therefore the momentum p for a particle is equal to mv. But if it is for the wave, the corresponding momentum is equal to h over lambda, just according to the Broglie hypothesis. So here we are emphasizing on the possibility for a wave to behave like a particle or a particle to behave like a wave, and that is what we call the principle of duality. Now, the kinetic energy based on this Broglie hypothesis the kinetic energy, as we know, for a particle is equal to a half mv square. A half mv square. But if we now take this possibility for a wave to have a momentum, you can see from here that v is equal to h over lambda m. That is, you divide both sides by m. So if we come here and say wherever we see v in our original formula, that is a half mv square for the kinetic energy, if you remove the b and put this, that is h over m lambda, the kinetic energy formula will end up being p square all over 2m, or when you remove the v and substitute it with h over m lambda, your kinetic energy will be equal to h square all over 2m lambda square. For you to do this, just write the formula for the kinetic energy, half mv square, and wherever you see v, substitute it with p over m. You will get this relation, and wherever you see v, substitute it with h over m lambda, you are going to end up with this formula. So the kinetic energy also is now possessed by a particle that is, wave that is behaving as a particle. And they said if this de Broglie hypothesis is correct, then we have a stream of classical particles, and they should show the evidence of wave-particle duality, because you can see the kinetic energy and the momentum. They are all properties of wave, of a particle, but now we have a wave of certain wavelength having kinetic energy and of course having the momentum, as we have just explained here. So we now come to standing de Broglie waves. That is, we are now going to examine an electron which is inside a box with an infinite potential. That is, the height of this walls of this box, they have infinite potential, meaning they have infinite voltage. They need infinite voltage for this electron to be able to jump out of this box. And of course, we assume the diameter of this box is the length from 0 to L. And of course, if this electron cannot possess, and actually it cannot possess that infinite potential for it to be able to go out, what it will be doing is to be hitting the walls continuously. Hitting the walls of this box continuously, and if that happens, it is going to establish a standing wave inside the box, because the potential required is beyond its capacity to be able to jump out. So therefore, when it does that, as I have said, the length of the box is from 0 to L, so it can have different types of standing wave. You can have a standing wave where your knot is only 1, that is a half of a wavelength, where knot is equal to 2, we have 2 knots, that is the n is antinode. This is my antinode, I have only 1 here, and this is antinode here, and here I have 2. When n is 3, I have 3, 1, 2, 3. When n is 4, I have 1, 2, 3, 4, like that, up to 5 and the rest. So the value of this k, which is a constant, is equal to n pi all over L, where n, as I've just said, is the number of the standing antinodes of the standing wave. Let me start with the first one, where my n is equal to 1. So you can see that from here to here is half wavelength. Therefore, one wavelength is equal to 2 times L, because the standing wave we have, it has only one antinode, and it is equivalent to lambda over 2. Therefore, L is equal to lambda over 2. Therefore, lambda is equal to 2L. Now, if you come here and substitute n, you put 1, your k will be equal to pi over L. If you come to this one, we have a complete wavelength, meaning lambda is equal to L, and our n is equal to 2. If you put it there, you have 2 pi over L. Likewise, for the n equal to 3, n equal to 4, n equal to 5, we can find the expression of wavelength with respect to L and the value of k in each case. Now, what are the energies of this confined standing wavelength? As we have seen, we have this one with one antinode, 2, 3, 5, and the rest. So the total energy for a particular standing wave, depending on the number of antinodes it has, is equal to h square k square all over 2m. But if we go back here, you know that our k is equal to n pi over l. Therefore, my E should be equal to h square. Instead of k, I'll put n square pi square. This 2m is already there over l square, because our k is equal to n pi over l. So if you square it, it will end up giving you this formula. So let us assume we are considering the case where we have only one antinode. You know the n should be equal to 1. So therefore, I will have E1 is equal to h square. The n square is 1 square, which is 1. Then pi square over 2ml. Then if you come to that of n equal to 2, definitely here should be 4. If you come to that of n equal to 3, this should be 9. So that is why we concluded by saying that the energy of the nth number of antinodes of these standing waves should be equal to n square E1, that is multiplied by that of the base antinode where we have only one. So in each case, if you are looking for n equal to 2, you put it. That should be 4 E1. For 3 should be 9 E1 and the rest. So from there, we can now say, let us compare the standing wave with respect to the energies. And if we use this formula we have just discussed, we said En is equal to n square E1. You can see that when E is equal to 1, it should be just E1. When E is equal to n is equal to 2, should be n square, which is 4. N square for 3, 9, for 4, 16, n for 5, 25. And we have said the general formula is n square times E1. So as we move further, we study this particle in a box where we said it has infinite potential, and we have seen that it establishes wave functions, and the general equation for those wave functions, y of x t is equal to a sine kx sine omega t. And our particle we have just studied in the box, it represents the stationary wave with different antinodes, as we have seen. For n equal to 1, 2, 3, we took up to 5. So the wave function sigma x is equal to a sine kx. That is, we take this one as our wave function, ignoring the frequency at which it operates, where this a is a constant, and of course, as we know from our elementary physics, it should be the amplitude at a particular time. Now, if we want to interpret that wave function, we know that the wave function of that particle is related to the probability density function. That is, probability of finding that particle in a particular region where that wave function exists. And the probability of finding it, you have to take the absolute value square of the wave function with respect to x. That is, when the particle is expected to be found from x to x plus delta x, that is small increment in the value of x. And of course, the probability of finding the particle somewhere, if we say somewhere, we mean from minus infinity to plus infinity, the probability should be equal to 1. That is, in the entire space, it is very, very necessary for us to find a point where the particle exists, and therefore, if we integrate with respect to infinity, from minus infinity to plus infinity, you are going to have your probability to be equal to 1. But if you are given a certain range, then it is possible within that range a particle exists and it may not exist, since it is probabilistic condition. Now, if you want to apply what we call the normalization condition, it will allow us to find the unknown constants in that function we have just seen. And for a particle in a box, our wave function psi of x, which is equal to a sine kx, we can now say k is equal to n pi over l, as we have just seen for the particle in a box where we have a stationary wave. So the function now a equal to sine, instead of k, we have n pi x over l. So as we have said, for the infinity, if you want to integrate from minus infinity to plus infinity, you have to find the particle. Therefore, the probability is equal to 1. So now, since we have changed the limits, we are no longer taking the infinity, but we are taking from x equal to 0 to x equal to L. If we normalize it as we have just seen here, we remove our k and put its value, n pi over L. We can now say our integration is from 0 to L, not from minus infinity to plus infinity, and still the probability within that range, if you normalize, it's still equal to 1. Now, that is the repetition of just what I've just said, and this we said is equal to this. So if you square it, you can see that this a here should be square and it will go out. Then the sign should also be a square, as we can see here. And we said the integration of this from 0 to L is equal to 1. And if you want to find the final solution, you find that your a will end up being equal to root of 2 all over L. So the next thing is we have to take note of some points. As we have just seen, we have treated the wave in a simple one-dimensional plane. But whenever you want to look for a wave or look at a wave considering all the 3 dimensions, that is x dimension, y dimension, and the z dimension, the analysis will be somehow complicated. And for us to be able to do that, simply we have to use what we call Schrodinger wave equation. And the Schrodinger wave equation is given by this relation. As you can see, the mass is considered because we are looking at wave-particle duality, and of course the Planck's constant is also present. And this equation has 2 segments. This segment where we have second derivative of the wave function, and here where we don't have any derivative of the wave function. The one with second derivative, we call it the kinetic energy components, and the one that doesn't have any differential is what we call the potential energy component or term, and the summation of the two will give you the total energy of the wave function. And here, since we said we are looking at it from the point of view of all the 3 dimensions x, y, z, so the wave function will never be the one that is confined within a box, but rather we can have a wave trying to even penetrate the wall and go out, as you can see here. This is the wall of the box ranging from 0 to L, as we have just treated, and the wave function is not being confined within the box, but rather it is going outside the box. And the ones that are coming outside the box, we call them leakage, the waveform leakage, and the particle that has finite probability of being found within the barrier. Yes, the normal for a simple one is within the box, but now you can have the particle going outside. And for a classical analysis we have done, this coming out is forbidden, but when we take the complex, that is where we have x, y, and z dimensions, it is possible for you to find a wave penetrating the wall. And that is taking us to what we call the tunneling, because tunneling is one of the chapters we are expected to look at in this quantum mechanics. So the penetration of the barrier is what we call the tunneling, and here we are assuming that we have a wave function that is traveling toward a barrier which has a length from 0 to L. And in a classical physics, actually, whenever it hits this wall, it has to be reflected and go back. But in reality, if you come to quantum mechanics, there is possibility of tunneling, that is for it to penetrate into the barrier. And even within the barrier, it can strike the other wall and go out. But one thing we need to understand is whenever you have a wave penetrating a barrier, the moment it penetrates, the component that goes in is the one that passes, but part of it will be reflected back, and that is why there must be attenuation in its amplitude. You can see that the amplitude of this one before going into the barrier is much bigger than this, and when this one also tries to penetrate the second wall and go out, you can see further diminish of what? The amplitude. So this penetration, the ability of the wave to pass through the barrier, is what we call the tunneling. And of course, in quantum mechanics, it allows this to happen. But in the classical mechanics, it is not possible for it to pass through the brick walls. If we say brick walls, we don't mean brick wall in reality, but we are saying any barrier, to penetrate any barrier. So if you want to solve that Schrodinger wave equation that has two components, that is the kinetic energy and the potential energy component. So if you want to solve it, we assume the barrier potential is equal to 0 as a function of x, and the x is having values from 0 to L. So that our equation will now be like this. This is my kinetic energy component. Look at it, and it is the one I have here. And of course, if you want to go with everything, that is to collect everything here, look at it, we said this one equal to this. So now if you want to collect everything on one side, the first thing you will do, you need to multiply both sides by 2m. Therefore here should be multiplied by 2m, this one will be cancelled. Then you divide both sides by this h square. So finally you will be left with the second derivative, d square of this pi dx square. Then this one will have 2m e of this side all over h square, and if you take it to the other side, it will be equal to 0. All I did here is I multiplied both sides by 2m, divided both sides by h, and take all these components to the other side, and I got this equal to 0. So sit down and do it yourself. It is straight. Now if you find the general solution of this, how do we find the general solution of this? Go back to your mathematics that you've taken in 200 level and 300 level, where we have second derivatives and we can find their general solution. The general solution should be of two components, A with sine and B with cos. All these things are done in Maths 242 and I think 241 and 242, 200 level. So go and brush that. This is the solution as we have seen. And now if you apply the boundary condition, that is to say x is equal to 0 and b is equal to 0, then this component will go. Now I will be left with sigma of x equal to a sine this x. So whenever you set the maximum value of x is equal to L, so this x should be removed and replaced with what? L. And we already know that the energy is equal to this. Go back to the previous slides. So if you take this into consideration, you finally get the general solution equal to a sine n pi x all over L. So ladies and gentlemen, as I told you, this quantum mechanics is somehow complicated, but don't worry, I will make sure we find a solution of, a way of simplifying it. I advise you to go through this lecture again and again until you understand. If you have any problem, don't hesitate in contacting me for that explanation. Thank you very much. Till we meet in our next lecture.